So I'm Arindam Ghosh. I am from the Indian Institute of Science, which is just about 17 kilometers from here, to be exact. I run an experimental group there which works on various aspects of quantum condensed matter, particularly for graphene and other two-dimensional materials. Our goals have primarily been to look at topological aspects, how we can make electrical conduction happening, which are protected in nature. That's at least 30% of my group works in that direction. I'm going to present some of the experiments, hopefully give you adequate background for it. But before I start, can I have a look at how many experimentalists are here? All right. That's excellent for ICTS. I have seen far less number of experimentalists before. Good, excellent. But I shall try and connect more towards, give you an introduction for experimental situation, and then see what kind of theoretical background would lead to those experiments. So as I said, one of the major goals that we are looking at is that what way we can create electrical transport in these new materials and devices and systems so that electrical conduction happens without dissipation or resistance. Obviously, the first one came many years ago, which is, I'll give you a little bit of overview, and this is for more general audience, but let's go ahead with it. The earlier demonstration of superconductivity was essentially a revolution in instrumentation, and came because of the fact that Cavity-QED actually bought the license of the compressor that eventually from Tesla, Nikola Tesla, to make the helium leak detector, helium liquefier, which led to a discovery. Of course, then we moved on for a very long time, and what we had there is, materials started becoming more and more important, and the TC started going up. However, in 2000 and early 2000, we started looking at graphene. And as far as superconductivity is concerned, they started coming with very interesting new kinds of dissipationless flow. For example, if in case of graphene, you have a possibility of doping it to the, to 10% or 12% of the doping of the percentage of the electrons, and then in that case, it's theoretically predicted that you will be able to get new kinds of superconductivity, like a topological superconductivity, where the order parameter winds around in a d plus id kind of symmetry. Okay, I'm not going to talk about these at all, but these are experimental systems that we are strongly working with and trying to dope it sufficiently heavily so that we can achieve these new phases of matter. Okay, however, what has changed over the last maybe a decade and a half to two is the devices. The devices are becoming more and more smarter, and you're having access to new properties which was not possible before. And that's what I'm going to talk about today. Perfect example, which is of course a very old one, 1980 onwards, is the quantum Hall effect, okay? Where you have a two-dimensional electron gas, which has a Hall bar type system. This is a perfect case of a Hall bar for those who are not sort of familiar with this geometry of devices. And if you apply a magnetic field, then you do end up getting a zero resistance, longitudinal zero resistance states like these at sufficiently large value of magnetic field, which are essentially the Landau quantized levels. And this two-dimensional, this resistance going to zero is said to have a topological protection, and I'm going to talk about that in a while, okay? This is in finite magnetic field, but later in 2007 from Würzburg, there is another one which is extremely popular today, and that is the topological insulator related problems, where what you have, this was the original one, the cadmium telluride, mercury telluride quantum wells, where what you see here is that if the quantum well is very, very short or very thin, then you get a standard insulator, because and once you start increasing this quantum well thickness, then the resistance along this plane, parallel to this plane, the resistance starts becoming universal, and it becomes E square, 2E square by H. Now I'm going to show you why this is another manifestation of topologically protected conduction states in a two-dimensional system. This perpendicular parallel to this plane is a two-dimensional system. Okay, so this happens at zero magnetic field. Okay, now this is the fundamental of it, and we will need a little bit of it as we go along. But so I'll give you an introduction very quickly. So when we get a topological protection is when you have, imagine a system and which is 3 or 2-dimensional, and define a parameter called a topological invariant C. It's usually a system which has a non-zero Berry phase. That means you have a wave function which is a spinner, has 2 components, and you go around in the k-space over a full closed loop. And if you accumulate a non-zero geometric phase, that's Berry phase, and when you have a non-zero Berry phase, then you will have a what you call a finite topological invariant C. I'm going to go for more detail. And assume a system in which bulk has a non-zero C, but outside C equal to 0. So in which case, at the surface of this, the gap must close. And in 3 dimension, this will lead to protected surface states where the backscattering is prohibited, but not the other ones. However, in our 2-dimensional system, the situation becomes very different. For example, here, there's a 2-dimensional system where the bulk is gapped. There is no transport here at all, but the gap has to close along the edges. Okay? When the gap closes along the edge, then once I pass current, it cannot be backscattered, and hence it is destined to go along this distance, along this line. Okay? And hence, you will get a dissipation-less flow in this direction, and the 2 edges will have opposite directions. The conductance of this system now is entirely determined by its contact resistance, because there will be electrical contacts here and here somewhere, and hence the system conductance is determined by its universal contact resistance, which is 2E square by H. So that is the basic idea of having this topologically protected states in a system where you have a finite topological invariant C, and which is insensitive to weak disorder as well as interaction. This is exactly what has happened in the mercury telluride quantum wells, where because of unique property of the mercury telluride, which inverts the p-type band above the s-type band, something like this. Over here, this is a band inversion that takes place. You have the p-type band, which is of 1 spin polarization, which goes above the conduction band, and hence, if you go along the band, the pseudospin polarization essentially evolves, essentially effectively giving you a finite Berry phase into the system. The situation can be very nicely and very elegantly explained with in terms of Berry curvature. Here it is. And the Berry curvature is essentially simple. If you have, imagine you have a system, an electron going around an Aharonov bomb loop, and imagine the phase that it accumulates. Then if that is Berry phase, then Berry curvature is the effective magnetic field that has caused that phase. Okay? So if you think in terms of Berry curvature, then any kind of a spinner type wave function will have Bloch electrons and the velocity of the Bloch electrons has an additional component apart from the group velocity, an additional component of like this, which is because of the geometric phase that is accumulated while going around in the k-space. And that leads to a very interesting situation, because now you have the electrons can flow perpendicular to the electric field. You can see this k dot, which is equal to the electric field plus the additional term, which is effectively a Lorentz kind of term, that even if B equal to 0, then the movement of the velocity of the electron accumulates, has an additional component which is perpendicular to E. And this is what eventually leads to the edge modes. Okay? If you have a system where the inversion symmetry and the time reversal symmetry are both maintained, for example, if I have a time reversal symmetry, it is this, omega k is equal to minus of omega minus k, and spatial inversion symmetry, which has got omega k is equal. Oh, I'm really sorry about it. There will be no minus here. Please ignore that. This is spatial inversion symmetry. If both of them are maintained, then the omega k will be 0, which is a topologically trivial system. Whereas, if your time reversal symmetry is broken by this, then you have got a standard quantum Hall effect. Magnetic field breaks it. However, if you have got the spatial inversion symmetry broken, then you have got the Valley Hall effect. Okay. Now, this a beautiful example was given recently by the 3 years ago, nearly, by the Manchester group, where they kept graphene on boron nitride. Okay. The boron nitride has got boron and nitrogen, essentially almost identical crystal structure as that of graphene, within about 5% or so. When I keep graphene on top of boron nitride, you can see graphene is these black ones, and boron nitride is red and blue circles. Nitrogen essentially positions itself at the center somewhere here, okay? And that leads to a breaking of the in-plane inversion symmetry, okay? And that leads to what you call the Valley Hall effect. And the way we detect this, or they detect it, essentially you have a Hall bar geometry at 0 magnetic field. If I pass a current in this channel, because of the fact that the valley current is charge neutral, it can go in both directions along the edge and travel very long distances along the edge. And that leads to a non-local voltage, a voltage which you do not expect from classical Poissonian equation. Okay? So you have the non-local voltage generation, and that non-local voltage decays as you go farther and farther away, because the disorder at the edge is essentially dissipating the valley current that moves in both directions from here. Okay? So disorder of the edge is extremely important. Okay? That limits the flow of the topological current in these kind of systems, and which is why it's called marginal topological protection. In case of a standard topological insulator, you actually have a magnetic impurity which can break the topological protection. Here, a simple lattice defect which can transfer an electron from one valley to another valley can break the topological protection. Hence, it's not as easy to maintain the topological flow of current as in the case of standard spin orbit coupled topological. Okay? And this is what we are going to talk about. This is where what I'm going to show you is that what signature we will have when you play around with disorder. So I'm going to talk about edge modes in graphene, and I'm going to talk about two cases specifically. One is single layer graphene point contacts, where we will be showing how we can create extremely high quality edges. And I'm going to show you bilayer graphene, which is a very recent work, where I'm going to show you that if you have disorder at the edges, there's a new way of detecting edge modes which has not been done before. Okay, so first one first. I'm going to talk about, this has been very strongly influenced by my theoretical colleagues, particularly H.R. Krishnamurthy, Manish Jain, and Vijay Shenoy, and their students. Without their theoretical support, this work would have not have been possible. Okay. So the edge of graphene is something which is very, very common. It's known. Okay. The problem started nearly 20 years ago, when Millie Dresselhaus and her group, and there's a Japanese group as well, which came together and showed that edge of graphene has states which do not backscatter. Now, there is no topology there. Okay? So first part, there is nothing to do with topology as such. The second part, that will have significant component of it. All right, so if you have a graphene system, the bulk of the system is beautiful linear band structure. We all know about it, and the density of states varies linearly. And you have zero density of states at the K point, and then density of states increases as you go higher in energy. However, if you take a semi-infinite graphene, it's a very large system, and there are two types of edges. One is armchair edge, other is a zigzag edge. Now, if you calculate the density of states and the band structure of the armchair edge, then in that case, it turns out to be a simple semiconductor. We have a beautiful, gap opening up in the armchair. However, if you have take the zigzag edge, then in that case, you start seeing a very different kind of band structure, where a new type of zero energy state appears. There's, again, as I said, there's nothing called topology here, because all you need to do is calculate. So plain and simple tight binding model, you take the edge wave function and then assume that, this is one particular value, the other value is orthogonal, so you have to have zero wave functions, zero component here, and use that, and you will get the zero energy states. And this is what has been done. And this has been done by many people over the last 20 years. What seems to be the case is that if you have a band structure with zero energy state and you keep a Fermi energy somewhere here, then in that case, you have one additional state moving in this direction in this edge, and the other state moves in this direction on the opposite edge, leading to a perfect electrical conductance. This is theoretical prediction. Okay? Has not been observed so far. Question is, how can we do this? So people have started looking for edge states for quite a long time. By the way, quick point here, the interaction makes very interesting case here. The band structure splits into, and you get a gap in the density of states. Okay? Now, the experimentally situation is very, very different. You see, at the end of the day, to look at the edge states, we need to have two requirements. You need to have pristine edge. It's either zigzag or armchair, so that the electrons don't scatter to another valley. And the second thing is that you need to make sure that the bulk doesn't contribute to the transport. You have to shunt the bulk out. And in order to do so, most people try to open a quantum confinement gap. And hence, the best way to do this will be using carbon nanotubes, for example. That's what they started with. This is not transport experiments, but using scanning tunneling microscopy. They looked at the states along the edges. And as you can see, this is a beautiful image where the scanning tunneling microscopy shows that there is a large state available here than in the bulk. This is a graphene nanoribbon experiment, and this experiment came about 2 years ago. Experiment transport-wise situation is very difficult, and it was found that this is IBM group. They made these nanoribbons to increase the quantum confinement gap, but they never saw these experiments, the non-dissipative edges, simply because it was too dirty, edges were too disordered. And there were a lot of experiments, I'll not go through in that. This was the Nature paper in the last 2016 from the Texas group. They essentially showed that if you have a nanoribbon here with epitaxially gone graphene, then you will have very good quality transport, but that's not edge transport. Okay? You very high quality ballistic nanoribbons, but nothing to do with the edges. We essentially did this experiment by taking a different route altogether. We decided that, okay, the graphene edges can be maintained if you simply rip it apart. Imagine a hexagonal sheet of paper. What you do is simply tear it. And if you do so, it turns out the nature gives you the possibility of having pristine edges. And this was shown by the Berkeley group quite a while back, actually. And this is ruptured graphene, and it shows beautiful zigzag edges along for very long distances. We did a very simple experiment. We took a metallic tip, and we punched it to graphite like this. And then we pulled it up. That's it. We tore it. And while tearing it, we looked at its electrical resistance, and that gave us very interesting results. I'll show you in a minute. There were a lot of experimental details in it. This experiment took nearly three years, but I'm not going to go into that, but I'll give you the results. For example, what happens? Suppose, imagine, this is graphite. This side is graphite, and this side, there's a metallic tip. What I'm doing, I have banged the metallic tip on graphite, and I'm pulling it out. When I pull it out, I'm actually forming a bridge, a very nanoscale bridge, which is connecting the graphite and the metal. And I'm continuously calculating the electrical conductance along, across this bridge, okay? So when the bridge is very thick, this is the point of contact. When the bridge is very thick, I get very large current, and the conductance of the system is very large. If I pull the tip farther up, then the bridge starts getting narrow before it ruptures out completely from the graphite. Okay, and here is the narrow bridge. The conductance dropped significantly. I go farther up. I have now moved to less than 10 nanometer of the bridge. This is why it's called a quantum point contact. There is a bridge is extremely narrow over here, and then when I pull the bridge out completely, then it drops. What is interesting here, you can see that when I'm in this position here with the bridge is less than 10 nanometer, then my conductance is actually tending towards the universal conductance of 2e squared by h, okay? Not something which is arbitrary. And that's the key result of the work. what happened is this is gone, so conductance is 0. And this happened. This is a statistical experiment, but it happens all the time. So it's room temperature. You can see the conductance is hitting E square by H. At low temperature, also there are a series of conductances which have very similar kind of behavior. So the question is, what is happening? Oh, before that, as I said, it's a statistical experiment, so we did it a large number of times and see where do you get most of the conductance plateaus. And this strong histogram at E square by H shows that this is the 2 square by H of conductance, shows that in these systems of exfoliated graphene nanoflakes, you end up getting universal conductance just before the system breaks out, okay? All right, so this happens in all cases in different gas atmosphere, etc. We will not go into that detail. It's not a metallic break junction. There are previous cases of this sort. If you take a gold metal, you break it, you get a metallic break junction, but that's not the case here. That's because at this confinement, graphene is supposed to be an insulator. It's not a metal. It's a semiconductor. You open a quantum confinement gap of 60 millielectron volt, which is significantly larger than the temperature. The system should have become an insulator. It is not so. It's actually a metal with a very high conductance of 2 square by H. So, and what is interesting is that if you look at the tips, this is about 30 degrees, and which is very interesting because if you have got a 30-degree angle of the taper, it means that one edge of the tip or the contact is zigzag and the other edge is armchair. Armchair is semiconducting, zigzag is exactly perfectly metallic. Okay. And this is what our STM measurements also show, that we are making single layer graphene at an angle of 30 degrees of the apex. So that means one of the edge is a perfectly conducting edge. Okay. So this is the overall picture, what's happening. So this is a taper of the edges. This is, each of them essentially have this kind of stuff. At very large, in this region, this is the bulk bands. The Fermi energy is sitting in the bulk. So this region essentially is acting as a lead, whereas the actual edge current flows somewhere here. And this was recognized by our theoretical colleagues. And when the Fermi energy is in the bulk, which is in between the bulk band, the only conducting state is along the edge. Now, why there are multiple steps is because as you take the tip out, you start rupturing one after the other and essentially leading to stepwise behavior, which quantized in an universal manner. Okay. There are very interesting properties. I'll go in 1 or 2 minutes. Essentially, this is a gapped structure. If you do a non-equilibrium transport spectroscopy, DI/DV, then you get a peak at the two sides, and that there's a gap, which is very interesting because that seems to be saying that there's a strong interaction in the system. And from Manish Jain and his student calculated it translates to the on-site Hubbard interaction of approximately 0.25. UIT is about 0.25, which is slightly smaller than other experiments. Other experiments say about 0.5, but it could be a strong screening that could limit the conductance, the interaction. Okay. Very interestingly, if I apply a magnetic field, I completely destroy the universal quantization. As you can see, that's probably because you have the edge disorder here, which as soon as I apply a magnetic field, I localize my electrons along the edge disorder, and that leads to a strong localization due to the squeezing of the wave function itself. However, before I move on to the next topic, there's something really interesting, and I was really excited by this. This was pointed out to me by Vijay Shinoy and his student Adip. What happens if I continue to exfoliate or pull out graphene in a discrete manner, atom by atom? Will I have an effect of that in the experiment? It turns out to be yes. And suppose I do it extremely slowly. This is very difficult experiments. If I go to one atom, one flake which is connecting, one bridge, which is connecting the graphite and the tip, and I do it very carefully, then I see the conductances are quantized not just at one and then drops directly, but it shows a series of features at very low conductances. So what Vijay and Adip said that what could be the case here is that now the two edges are talking to each other, because the edge state, the state which is supposed to be a metallic state, is no longer, this is not a semi-infinite graphene, but this edge is starting to see the other edge. Okay? And this means that there is now a transmission, a reflection back, and hence the transmission coefficient is no longer 1 anymore. And they calculated it. They calculated beautifully. They calculated this resistance of this region alone by keeping this fixed, and calculated how much will the resistance be of this size as I change the number of hexagon on this side by 1. And they calculated, and we then put the results back on our data, and we found that now these states are essentially corroborating with 1 hexagon change on each side. As you exfoliate, the number of hexagons are decreasing 1 by 1, and each step essentially is giving us the number of hexagons that is connecting the flake to the leads. That was really neat, actually. So I'm more or less done with this part. I have what I have shown you here is that this is nothing to do with topology, but the edges of graphene are extremely interesting, and it harbors a non-dissipative edges, a state which can easily be destroyed by a strong intervalley scattering or disorder. But if you manage to make a system where the disorder is less, then you can have universal conductance, non-dissipative edge, even at room temperature. Okay? So I'm going to go to the next part. If there's a question, I'm happy to answer now. Okay. No, well, as a matter of fact, no, the only transport channel is along the edge. Okay. So as I come, so if you imagine this x-axis is the distance from the is the width of the contact. Oh, sorry. So this x-axis here, imagine that if I go in this direction, the width of this is increasing in this direction. Okay, so this is a parameter which is the tip distance. So this imagine as I go in this direction, the width of this is decreasing continuously, but the conductance is decreasing in steps. Okay, so what Vijay and Adif said that okay, what could be possible here is that these states are essentially discrete number of hexagons that is connected to your lead. As I pull my flake out, then I decrease the point contact size by unit of hexagon. I can't decrease it continuously. And each of those states is essentially giving the number of hexagons that is connecting this one, this flake or the bridge to the lead. Okay? Correct. Yes, but it decreases in steps. Conductance decreasing means this is the one side which is large tip, and this is the substrate. I'm creating a bridge which is a tapered 30-degree bridge between the two sides. Yeah. Correct. The channel, yeah, exactly. The width matters, absolutely perfect. It doesn't matter only in semi-infinite graphene. But the moment I make the graphene channel less than 5 nanometer or 10 nanometer, the wave function of the edges are actually going deep into the graphene in this direction. And it starts seeing the other edge. And that's when the wave function starts reflecting back. Yeah. That's correct, exactly. No, exactly, absolutely. Okay. Okay, so, I'm guessing there's no other question. Yeah, Sadiq. Correct. Oh, here, right? That's a very good observation, actually. Yeah, I think it's because of strain. I'm not 100% sure. Yeah, yeah. It's probably we are right now. We are actually stretching a hexagonal lattice of graphene. So it's probably that stretch which is giving rise to this behavior. Yeah, that's right. Absolutely. Yeah. Yeah, I mean, there are multiple bridges. It can be N. Yeah. No, that's the question Sadiq asked actually. So we don't see that structure because we do it very fast. We just don't see this. We see mostly this below 1 when we have just one left. Just one bridge left. They have gone off. They're torn apart. So there's the last one left here. Okay? Okay, so I've got about 7 to 8 minutes. Can I have 2 more extra minutes before to finish? So excellent. So I'm going to go to a more conventional work now, which is the bilayer graphene, and this is where topology is going to come into play in some way at least. This work is just about to be submitted, so work done by Ahmed, Paritosh, and we have been again very strongly collaborating with the theorists Rajdeep in TIFR and TV Ramakrishnan here and BHU. Okay, now bilayer graphene is very different. And this is something which was recognized in 2007-ish, that. You have 2 layers of graphene where the 2 layers are slightly shifted. That means A and B sublattices are not exactly on top of each other in the 2 layers. Now, the way this thing can be looked at is you can say that electrons in the lower layer all on the A sublattice is upspin, and electrons in the upper layer all on the B sublattice is the downspin. So the general wave function of the system is essentially a sublinear superposition of this, and this xi is nothing but the Valley index, whether you're in K or K prime gives you plus or minus 1. And hence this is a very similar, very nice spinor Hamiltonian, which means that the carriers in bilayer graphene will be chiral. But there's a little bit of difference from the standard single layer graphene system, where if sigma is a pseudospin, k is the electron momentum, but the vector here, gk, was originally I called it, this vector will rotate twice as fast as the position, as the momentum k. Okay, you take k in the cos phi in the plane, and you rotate it by phi, but this vector n will rotate by 2 phi. That means if I now go all over the K space, then the Berry phase that you will accumulate is 2 pi rather than pi in single layer graphene. Okay, now this gives you a beautiful Hamiltonian like this. I will not spend time much over here, but what I'm going to show you how the band inversion occurs like a standard topological insulator in bilayer graphene. So you have 2 layers of graphene, which if you don't have any communication between the layers and there is no electrical potential between the layers, they are essentially 2 Dirac cones sitting right on top of each other. Now, if I apply a voltage between the 2 layers by applying electric field across it, then you have shifted these 2 Dirac cones, and hence 2 layers are overlapping in this fashion. Then I start tuning on the interaction between the two layers with a hopping integral of T lambda. And then you see that there will be a parabolic, the bands in bilayer graphene are parabolic, at least at large distances. And then you have a little bit of conduction band of a valence band of the lower layer here is sticking to this over here. So this is now a very similar situation. If you apply to a very large coupling, then you go in this direction, but experimentally in real system, we mostly deal with this situation where a band inversion has occurred in bilayer graphene in the presence of a strong electric field and interlayer coupling. Okay, now that means that we will have very similar kind of transport that people have seen in the case of topological insulator or the inversion symmetry broken single layer graphene. And indeed, I'm really sorry about it, but I put the references, but it's gone. It's the 2 groups published this work in 2015, and they showed that if I have a bilayer graphene and apply a large electric field, exactly the way the non-local voltages are generated in single layer graphene over here also, we get a very strong non-local voltage generated when I apply current here, and the valley current moves in perpendicular direction and produces voltage completely separate places. Okay. There are many other experiments which actually showed that similar behavior happening at graphene grain boundaries. Bilayer graphene grain boundaries are very interesting because you are changing the stacking of A and B that will lead to a change in the topological invariant, and that will lead to very large, beautiful non-dissipative flow along the grain boundaries, and that has been already observed by several groups. The question that we asked is that, okay, now forget about the internal defects, what about the edges of bilayer graphene? And recently, actually this year, the Manchester group came up and said that, okay, we put superconductors at the two edges of bilayer graphene. I apply an electric field, so I gap the bulk of the bilayer graphene like this, using two gates. There's one gate on top, there's one gate at the bottom. I apply an electric field, and the bilayer graphene edges the gap is completely gapped out. The bilayer graphene is gapped out. Then I have two superconductor, and these superconductors, when they are injected Cooper pairs, then there's a coherence all over the system, and that leads to a supercurrent interferometry. So what happens is they came to a conclusion that in the gapped bilayer graphene, the gap is far more insulating than the edge. Okay? The current actually flows along the edge rather than through the bulk. And that was very interesting. And they claim that edge current shunts the insulating bulk in the gap layer graphene. Very similar to what happens in topological insulators, but there, of course, it's nearly E square by H, nearly perfect conduction. Here it is not so. So the question that came up and we started looking at is that how to detect the edge modes in conventional bilayer graphene devices. Gap it and then see are there edge modes. The difficulty is that the gap and the edge both localize simultaneously. Because when I apply an electric field, I'm gapping out the bulk, whereas the edges are being localized by the disorder at the edges. Okay? So both localize, and that's what was essentially shown in this theoretical paper way back in 2011, and showing that gap is bulk, but the edge is also insulating. So it becomes very difficult experimentally to say, okay, the gap is, the electrical transport is occurring whether through the bulk or through the edges. So we asked the question, is there a probe? Is there a probe which can tell me exactly where the conduction is taking place? So answer is yes, they're a very interesting probe, and that's called self-averaging. And this is new. So imagine a system which is localized in 2 dimensions. What happens is the electron hops through systems, through states. If there is a large gap somewhere, the electron will bypass it and go somewhere else. I can easily bypass large areas where there are no states. Okay? So that's why in 2 dimensions, you get something, you get self-averaging of electrical conductance very easily. As you make the system larger, the effect of large resistances actually decrease. In case of 1-dimensional, that is not possible. I'll take about 5 more minutes. So in the 1 dimension, it's not possible. What happens is 1 dimension is that you are forced to be in this direction. You cannot move in the insulating bulk. So there's an unavoidable high resistance hop, which actually completely destroys the effect of length of the system, or the system size. Very quickly, if I have a quantity, which is a thermodynamic quantity, its fluctuation must go to 0 at large enough scale. Okay, so that's called self-averaging. So if in a case of a localized electron system, it is the log of G, where G is the conductance in the unit of 2 square by H. If I were a localized system, then what happens is, in the higher dimension, it goes as 1 over LD, L to the power of D, whereas in 1 dimension, simply because you cannot avoid these large resistance hops, this number decreases very, very slowly as a logarithm. So this is a beautiful way of, which is dimensional effect. Okay. So this is what we looked at very quickly. So this is the conductance of a bilayer graphene. As you can see at the charge neutrality point, the conductance can be very low. It can actually be 3 orders of magnitude low at low temperatures. This is the conductance of the bilayer graphene. And what we did essentially, this bilayer graphene, we looked at its transport for different length L. And this is one of the particular devices where it shows very low length, very low conductance. I'm going to skip through it. But what's interesting is that as you go to, as you change the density, this conductance goes through series of very reproducible hops. So these are oscillations. These are essentially realizations of different disorder profile, okay? So this is, each and every point here is an ensemble, which is changed by, as I change the electron density. Okay? There are 4 sweeps, and they all fall on top of each other. These are not noise. These are actually electrons are facing certain resistances, the different ensembles. Okay, so what we do is that we calculate the mean of conductance and the variance of conductance and look at the self-averaging property. I'm going to skip a little bit. What's interesting here is that if you are metallic, that is the conduction band, the Fermi energy is in the conduction band, the probability density of the conductance fluctuations is beautifully Gaussian. But when you're in the localized regime, that is the Fermi energy is in between, inside the gap, then you have log normal distribution of conductance, very well known in the case of localized systems. And from there, we calculate the width and mean of the distribution. And this gives us some very interesting results. This is the variance of log G, which increases slightly, and this is the mean of log G, which decreases with as you increase the length. This is the most important part of the result. I'm out of time, so I'll quickly finish it. So if you have got a small band gap, so the transport is very strongly being affected by the bulk of bilayer graphene, then the self-averaging is clear, that it comes down. As you increase the length of the system, the relative fluctuations come down very fast, and this goes as 1 over L square, as it should be in a bulk 2-dimensional system. However, if I make this band gap large by applying a large electric field, now I can see as you increase the length, this parameter doesn't decrease at all, almost nothing at all. And which essentially goes as, this is, of course, a statistical experiment, so there would be a lot of noise, but it's very easy to see that this sharp dependence at low values of D is absent in the case of large values of the band gap. That means essentially we have a 1-dimensional transport. This is 1 over log G with the experimental error. This is just a guide. It shows that the localization in bilayer graphene, which is strongly gapped, is not a 2-dimensional localization, but is most probably a 1-dimensional electrical localization. That's my last slide. What happens in this case is that you have we can extract the localization length, which turns out approximately half a micron, which is significantly larger than the localization length in this direction, but it actually corresponds to the property of these strong localization length along the edge in this direction, okay? And that has been already shown from STM measurements, that this is the number of between strong defects along the edge. I'm going to finish it here. So what I would like to summarize by in this part of the talk is that we have looked at weak self-averaging, where the log of conductance decreases, the fluctuations and the mean ratio decreases very slowly as you change the length of a bilayer graphene sample, which is one of the most distinctive effect of 1-dimensional system rather than 2-dimensional system that you thinking. Okay? The localization length is nearly 500 nanometer, even though the gap-induced localization length cannot be more than 5 to 10 nanometer. And hence, the localization length is not governed by anything to do with gap or electric field we apply, but it's because probably the large amount of disorder that is going along the edges. Okay? And we have seen from our early experiments that the conductance, that the edges are very strongly interacting. So we have a very interesting system now where the localization is happening along 1 dimension in the presence of very strong interaction. So we do not know whether this could lead to some other possible implications, both experimentally and theoretically. So I would like to stop here. I would like to acknowledge the Departments of Science and Technology for all this research, and I thank you for your attention. I'm sorry for a few minutes extra, but
thanks. Questions?
Over here. For the quantized conductance measurements, can you measure a subband spacing by taking finite bias data, or is this too fast of a process when you stretch it out?
So that's a great question. As a matter of fact, if we go to different conductance levels and do the non-equilibrium spectroscopy, there is no subband spacing, because there is no subband apart from the edge. There's only one mode along the edge. So we actually do not see the kind of standard features of the peaks of coming in and going up, splitting, band splitting. Those kind of features are completely absent in these kind of systems because there is just one mode. So no, answer is we do not see any subband spacing.
So what do you mean by gap-induced localization length? I mean, I didn't understand.
Okay, so essentially because what you have here is, this is strongly gapped, right? So you can calculate what is the width of the wave function which is going into the gap. And that is given by this simple expression, which is essentially h cross over. This is the gap. The delta is the gap that I have opened up by applying a very large electric field perpendicular to the plane of graphene, bilayer graphene. So the width of the wave function in this direction cannot be more than 5 to 10 nanometer. But the localization length that I'm getting from the experimental fitting is in the order of 500 nanometer to 1 micrometer, which is about 30 to 40 times larger, about 100 times, 500, yeah, about 100 times larger than this length. That means the bulk of the system cannot contribute to the electrical transport that we observe.
Any more questions? Okay, so if not, let's thank the speaker.
Thank you.